What you want to do is make sure you understand the stuff, you know, where we left off, at least up to that point where we left off. That way, you don't get to the point where you're studying for the exam and realize that it doesn't make any sense. And so you want to, if something doesn't make sense, then you'll want to make sure you ask, you know. Normally what I do is if something was confusing, let's say in a lecture, I'd go home and then kind of go through it and try to find additional information. I look at other books and stuff. When I was at a student at UCLA, you know, what I often did was I'd go to the bookstore. You can't do this anymore. And I'd look at the next advanced class. And sometimes the questions were pulled out of an advanced textbook, you know, like the next class in the series. Sometimes you could find the answer there. But they don't have textbooks anymore. I was there at the bookstore. They're all, you can't access them. But there are other sources you can find. But what you want to do is you want to see, and if it doesn't make sense, then you want to try to ask, like at the beginning, you know, that didn't make sense. How did you get 9? You know, or you ask your neighbors. But you don't want to just wait until the night before the test and realize you don't know how you came up with 9. And so the most abundant one was the H1, 016, H1. And so, I'm sorry, can you tell me how you did it? How you got the percentage?
Yeah, so for like that one, I remember like that came up, and I found that was when you just took the H1 and substituted it over.
Okay, what did you do with the percentages? Because we have the H1 percentage here. Let's take a look. It's 99.9885%. So you took the 99.98, what was it? 85%. You squared it? Okay, and so times 99.9885%. I see a potential problem here. Because the units here are going to be percentage squared, which doesn't have any meaning. Yeah, okay, so we could try to get rid of the percent squared by either converting it into decimal form or fractional form.
You could just choose to put like the oxygen as percentage and the other hydrogens as fraction.
Yes, okay, that's a good suggestion. We could put the oxygen as a percentage and leave that there. It's 99.757. So this is going to be 99.757%. So if we leave this one and get rid of these two percentages, then we're okay. And there are two ways to convert percentage into a different form. One is just to go fractional, or the other is to go decimal. I'll just go fractional here. And so now this doesn't have any units. We can convert this back into percent by multiplying it by 100%, but we're not going to do that. And then this is going to be like this. So this comes out to 99.757%, but the way we read this is like this. The way I read this is 99.9885 out of 100 will have H1 out of this percentage. So out of this percentage, how many will have H1 on the left? And then out of this percentage, how many will have H1 out of the right? Because the other choice was an H2. An H2 had a 0.0115%, or 0.0115 out of 100. And so we have to make sure that we have a choice for the left hydrogen, and the choice is, if we pick this choice, it's going to give us a 99.9885 out of 100 chance of getting it. If we pick this one on the right as an H1 as well, that's what we're going to get, times 100%. Now the units will work out. This is, I didn't give you the formula for this or equation for this, but this would be the equation for figuring out the percentage. And this is actually correct. Somebody else had mentioned that what they did was they added the two together, or added the three together and then divided by 3. But when you do something like that, it's not going to add up to 100% in the end. That's one way you can see if you have the correct answer or not. And so by doing this, then you got the answer. What was that answer again? Well, actually, why don't you just punch this in your calculator and see what you get? 99 point. 99.727%. Is that correct? How many sig figs are we allowed here? We should be allowed 6 sig figs. So give me one more digit. Oh yeah, 016 is 5 sig figs. But give me 6 sig figs because what do I want to show at the end? I want to see the rounding step.
After the 2 7 zeros.
2708. Okay, so we'll just go with this, and then we drop the 0.
Well, it's because the number after the 0 is a 7. I don't know.
We just want to show the drop digit, and it doesn't matter if the number after the 0 is a 7. Should I round up the 0 to 1? No, I'm only allowed one rounding step. I can't have a cascade of rounding.
Oh, okay. So
Okay.
It was after the 0 7, it was a 5.
After the 075, we don't do cascade. Only one. We drop that digit. We don't round anything. We just drop the digit. If the drop digit is 0, we leave it. Let me just double check. So I have 99 or 0.999885. I'm going to just square that times 99.757. I got a slightly different answer. I got 99.734. You guys got that too? Oh, you got that? Okay. So when we make an error in the lab notebook, we just cross it out with a single line. And the drop digit, it doesn't matter if there's a 5 after the 0. We don't do anything. So let's say you had, I'm going to move the decimal place over here. So let's say I had 100,000 water molecules. And what that would mean is 99,734 of those would be this one, H1O16H1. How much does an H1O16H1 weigh? And so, did somebody calculate that? 18.02 is how much the average water molecule weighs. But this is not the average molecule. So the answer is it 18.02? Well, we know that water's molecular mass if I had a water molecule like this, the average one weighs 18.02 U per molecule, or 18.02 grams per mole of molecules. All right, so this is quite nice because we could either use U per particle or grams per mole of particles because of the way what was defined. We could use either of these two units for the same number, and the reason we could do that is because of how the blank was defined. Based on the definition of the oftentimes we don't even write units here. Oftentimes we don't write units here because it could be in either of these two units. So you pick whichever unit you want. And that's because of how the mole was defined. And that's why it came out, Avogadro's number came out as a strange number. Well, anyway, getting back to this is an example of just dimensional analysis. We want percent at the end, so we have to tweak these other two, otherwise we're going to get percent cubed. Sometimes you get hit with dimensional analysis. Did I talk about the engineering class I took? Yeah, all right. And so this is the same kind of situation. You just try to figure it out. And then the way you can check your answer is you got to make sure everything adds up to 100%. And so the situation is, we can go on to the next one here. Oh, actually, before I go on to the next one, I want to figure out how much it weighs. Did anybody calculate the mass of this? H1O16H1. Now, when we calculate the mass of hydrogen is 1.007825. So we have two hydrogens at 7825. And now the units can either be in U per hydrogen atom, H1, or grams per mole of hydrogen 1. So if I had a mole of H1s, it would weigh 1.007825. However, if I have a mole of hydrogens, how much would it weigh? Well, we go off the periodic table, it's going to weigh 1.00794. Why the difference in mass? Because here, this is 2 times 1.00794 U per hydrogen atom. Up here, it's 1.007825. Why the difference?
Different isotopes?
Yeah, this is for just one specific isotope, and this number here is for the weighted average of H1 and H2. So this one's very precise. This one down here depends on the percent abundance. How abundant is H1? How abundant is H2? Do you guys remember doing the calculation for this? That is the average hydrogen. In other words, did you guys review some of this stuff earlier? The average mass of the hydrogen is equal to the percent abundance of H1. The percent abundance, I'm going to write that as fractional form. This is also dimensional analysis. 99.9885 out of 100 is H1. H1 weighs 1.007825 plus 0.0115 out of 100 is going to weigh twice as much, roughly. And the one is going to be 2.014102. Times 2.014102. Okay, and this gives us our 1.00794. All right, and the units here are going to be U per average hydrogen. Is there such thing as an average hydrogen? I mean atom? If you had a bucket of hydrogen atoms, could you pick one that's going to be the average? No, it's either going to be an H1 or an H2. Or grams per mole of average hydrogens. So this is just the average water molecule. If you had a bucket or a glass full of water molecules and you tried to pick one that weighs 18.02, are you going to find one that weighs 18.02? No, you aren't. You're going to find one. But if you take the whole collection and then just average it, then it should come out close. All right, so we have two of these H1s plus an O16. O16 we can't get off the periodic table. We have to use this table. What was this table called again? Yeah, this is a table of isotopes. And this table of isotopes I pulled from your Appendix D of your book. So it's 15.99, 49, 15. And so the mass comes out to what? And so let's go ahead and add it up. It's 2 times 1.007825 plus 15.994915. And this comes out to 18.010565. Now the sig figs for addition and subtraction depend on decimal places. So if I multiply this first one by 2, I'm going to get 2 point whatever to 7 sig figs, which is going to be 6 decimal places. So I have 6 decimal places plus 6 decimal places. I'm allowed 6 decimal places here, so I'm okay with this. And so the units here are going to be U per molecule or grams per mole of these molecules. And this molecule weighs slightly less than the average. It weighs slightly less than the average because, one, it's the lightest of the water molecules. And then, two, it's also the most abundant, so the average is just slightly less. The average is going to be heavily biased towards this molecule because this molecule constitutes 99.7% of all water molecules. Does that make sense? So what we do is we continue on, but let me tell you, there's going to be a problem. I'll just tell you in advance. There's going to be a problem when it comes to this. Now, for the first hydrogen, we say we're either going to grab this out of the bag of hydrogen atoms, we're going to grab an H1 or possibly an H2. But the probability of grabbing that H2 is much less. What is the probability of grabbing that H2? It's actually quite a bit less. It's going to be, where am I? It's going to be 0.0115 out of 100. And so anyway, let's go ahead and, if I move this 4 decimals over, and I move this 4 decimals over, then that means 115 out of a million. 115 out of a million is what we call 115 parts per million. So out of a million hydrogens, there's only 115 of them. And so that's the chance I'm going to grab that one. However, since we're doing the hydrogens first, let's grab the other hydrogen. The other hydrogen will make an H1. The other hydrogen is going to have a much higher probability. That's going to be 99.9885 out of 100 chance of grabbing this other hydrogen as an H1. And then we're going to go with O16. O16 is going to be the most abundant. This is going to be 99.757. 99.757%. And so this gives us the percent natural abundance of what? And so that's going to be 0.0115. The reason I don't convert it into decimals, sometimes I make mistakes. And so it's easier for me just to punch it in the calculator rather than moving the decimal in my head. Times 99.757. This comes out to 0.0114. Now, how many sig figs am I allowed here? I'm only allowed 3 sig figs, so I'm going to go 1147 percent. And so in fractional form, this would be 0.01147 out of 100. Actually, I'm only allowed 3 sig figs, so I'm going to round that. I'm going to round this to 0.0115 out of 100. Did you guys get the same number? All right, then what I'm going to do is I'm going to move the decimal place over. Let's move it 4 over. And so I'll move this one 4 over. And so again, this would be 115 out of a million. It's odd because it comes out the same as this. So it's just slightly less than 115. All right, this one's going to weigh a bit more. You know, not twice as much because, you know, this is 2.0. What was it? 2.014102. Plus the oxygen 16 is 15.994915. Plus the hydrogen 1. The hydrogen 1 is 1.007825. And so how much does this weigh? This is going to weigh 2.014102 plus 15.994915 plus 1.007825. And this weighs 19.016842. Okay, again, the units are going to be U per H2O16H1 or grams per mole of H2O16H1 molecule. All right, so what we can do is we can start to generate what's called a mass spectrum. A mass spectrum is the output from a mass spectrometer, and a mass spectrum should show all possible. Sometimes the molecules break apart and they'll show additional fragments, but this is the ideal mass spectrum. Sometimes we don't have ideal things, mess things up, like the molecule gets fragmented when we try to ionize it, just a little too roughly. And so the lightest of these will appear over here on the left. You know, these will be deflected the most. And the lightest one is going to weigh in at 18.010565. And so we get a peak here at 18.01. Actually, 0565. Here. And this is going to be the biggest peak, you know, because if I look at the relative abundance, it's going to be 99.734%. So this one's going to come in 99.7347%. 734. Oops. 734. Okay, then I'm going to get another peak here at 19.01684. So over here, 19.01684 and there's going to be a tiny peak here. Now, what is the percent abundance of this peak? The percent abundance of this peak looks to be 0.0115%. Okay, now if I build this molecule, that is, let's say I grab a hydrogen and it comes out H1. And then the oxygen came out as O16, but the second hydrogen I grabbed was an H2. Will this weigh the same amount? Yeah, this is going to weigh exactly the same amount. How much is it going to weigh? It's going to weigh 19.016842. It's going to weigh exactly the same. And so it's not going to result in a different peak here, but you know what it's going to result in? It's going to result in a different way of making this hydrogen. So the first hydrogen I grabbed out of the bag was H1 here. What's the percentage of that? The percentage of that is 99 point, should put these on a piece of paper here so I don't have to scroll back and forth. 99.9885. That was 99.9885 out of 100 chance of pulling that. And then the second hydrogen, we'll just do the hydrogens first. So this is the first hydrogen. The second hydrogen I'm going to grab is an H2. There's a 0.0115 out of 100 chance for that, times the oxygen 16, which we'll just leave as a percentage. And the oxygen 16 was 99.757%. And do you know what this is going to come out to? 0.0115%. Now, what do I do with this percentage here? And so what I have to do with this percentage is this. This first 0.0115% is for making H1O16H2. And then what I need to do is I need to add the second percentage to that. The second percentage is going to be 0.0115%. And this is for making the H2O16H1. So there are two ways of making this molecule. One way is to grab the hydrogen 1 first. The second way is to grab the hydrogen 2 first. We have to account for both those ways. And what that's going to do is it's going to double the probability of making that. And so rather than being 0.0115% for this peak altogether, we have to double this. So it's going to be a 0.0230%. And so,
That's not really how it occurs in nature, is it?
no, this is how it occurs, and nature is random.
Yeah.
And so we have to account for the probabilities there. It's a random process. In nature, there are two ways of making this molecule. One is randomly pick the H1 first. The other is to randomly pick the H2 first.
I just think that there's not really a difference if like you were creating a mass.
In the mass, no, you aren't going to see. This is just going to be one peak. But the probability of this, or the height of this peak, is going to be 0.0230% total for making this. Okay, so for the ones, etc., we can just continue here. What is going to be the heaviest, and what is the probability of finding that, and what is its mass? So there are going to be more peaks here, and then tell me what the heaviest one is and what the abundance is for the heaviest one. All right, I'm going to pause this for right now and then let's here. Let's see. Yeah, I forgot to record that, but sorry. I don't know if I recorded this doubling here, but you should have that in your notes. So this one we had to double. Why did we have to double it? Two ways of making it. This one, are there two ways of making this? No, there's only one way, so we don't double it. And so if we do this for all these percentages better add up to 100%. But you have to watch out for rounding error. And so when we double check this, we carry extra digits here so that it rounds. Like for example, I wouldn't round 99.7 to 100%. Obviously, it's not going to round. There's going to be a round off error, and it's not going to add up. All right. The next calculation I want you to do is to use the mole concept here. And this one's not the rarest, but we want to see, like, for example, this would be a sample calculation here. Let's say I have a glass of water. This glass of water is 250 milliliters of water. And the question is this: how many H2O18 H2 molecules, if any, would you expect to find in this glass of water? And the second question is, how many U of H2O16 H2, and how many grams of H2O16 H2 is this? So this is using the mole concept. We talked about the mole, Avogadro's number. What's Avogadro's number again? And how many sig figs is this now? This is new. It's infinite sig figs. That's new. All right, so why don't you try these? These are some examples of dimensional analysis. Now, as this week, this is week 2, we're going to get into chapter 3. And so what I want is, I want the number of H2O18 H2 molecules. But what am I given? Well, I'm given an extensive quantity of 250 milliliters of H2O. And this is not isotopically pure. This is a mixture of all the isotopes. However, the information that I have this, 2.71 times 10 to the minus 9% H2O18 H2 in water. And so when I think about this, I'm probably going to do this. I'll probably represent this as some fraction. Although percentage is not so great. This is going to be 2.71 times 10 to the minus 9 out of 100. This would probably be better expressed in parts per billion. Let me just do that as a side. 2.71 times 10 to the minus 9 out of 100. So I can convert a fraction or decimal into whatever I want. And I'm probably going to do part per billion by multiplying it by a billion ppb. If I do this, 10 to the minus 9 times 10 to the minus 9 gives us what? 10 to the 0, which would just be 10. And so this would be 27.1 out of 100, or 0.271 parts per billion. I don't want to do parts per billion. I'm going to do parts per trillion. And so I'll just multiply this by times 10 to the 12 ppt per trillion. And so you can punch that into your calculator if you want, or it would be, this would be 10 to the minus 2, bring that up, that's 10 to the minus 7. Did I do this calculation correctly? It's 10 squared, 10 to the minus 2, yeah, 10 to the minus 11. This would be 10 to the minus 2. Maybe I didn't. Is that what you guys got? Or did I screw up the calculation? Sometimes when I do calculations in my head, I screw it up because I'm thinking maybe not so carefully. So times 1 times 10 to the 9th divided by 100. Yeah, I did screw it up. So I did it in my head again, and I got a different answer. And so this comes out to 2.71, so I moved that there. In fact, let's just cross these out. 0.0271 parts per billion. Is that very convenient? No. That's why I'm going to parts per trillion. Do you know what this is going to be in parts per trillion? 27.1 parts per trillion. So that's more convenient. And so what this says is if I have a trillion water molecules, how many of these will be H2O18H2? 27. So 27 out of a trillion. I can't have a fractional molecule, and so I have to keep moving the decimal over to clear the fraction, or the 0.1, 1/10 of a molecule. I can't have that. But I'm going to retain it because I don't want to go to parts per. What's after a trillion? So I'm going to stop there. All right, so this is our conversion factor. This conversion factor is the same as this one here, but I'm going to use this one because maybe physically it might make more sense. So what I need to know is how many water molecules. If I have a trillion, then I'll have 27. But in 250 milliliters of water, I have way more than a trillion water molecules. Way more, trillion upon trillions of water molecules. Probably more than that. And so how can I figure out how many water molecules are in 250 milliliters? Well, I'm going to go from milliliters to grams. So I'm going to say I'm close to 25 degrees C. If I'm close to 25, I'm just going to go 1.0 grams per milliliter. I'm going to be a little bit more precise. The closer we are to 4 degrees C, the closer we are to 1. Otherwise, what would I do? I have to look at the table. There are different ways. This is, we're going to say about, this tilde. About, or look up in the table, or graph it and get it off the graph, or use the equation. So, or look in table, graph, or calculate it using the law of density. The law of density is just an empirical equation that defines the density over temperature range. So we have to assume a temperature. And so I think I'm just going to use 1.0 because I don't want to look it up in the table. And there's already uncertainty in this calculation. Okay, now I have grams. Now what can I do next? I'm going to go to moles. And so we know the average water molecule, a mole of those are going to weigh 18.02 grams per mole. Okay, and then where I'm going to go? I'm going to figure out how many average water molecules I have by using Avogadro's number, 6.022 times 10 to the 23rd molecules per mole of molecules. Okay, then if I know the total number of molecules, then I know I have 27 out of a trillion will be H2. And so I'll say 27.1 H2O18 H2 molecules out of a trillion H2O molecules. Okay, and so the units cancel out, which is what we want, and we'll go 250 divided by 1802 times 6.022 times 10 to the 23rd times 27.1. You just drank, if I did my calculation correctly, divided by what? Divided by 1 trillion. Divided by 1 trillion. And I get 2.26 times 10 to the 17 H2O18 H2 molecules. So how much does that weigh? Well, we know how much a single molecule of this weighs. And so a single molecule weighs 22.027364. So what I'm going to do here is I'm going to go 2.26 times 10 to the 17 H2O18 H2 times 22.027364. 3 extra zeros at the end. Okay, I better. Oh yes, I did. Shoot. I divided by a billion, not a trillion. It's a million, billion. I don't use trillion that much, so thanks for catching that. So I need to divide it by another 1,000. So if I divide by another 1,000, this is not going to be 10 to the 17. It's going to be 10 to the 14. Sorry. So let's correct that. This should be 10 to the 14. Correct that here. And then let me correct that here. This is 10 to the 14. And so a single one of these water molecules weighs 22.027364. And I got a lot. So 22.07364 U per H2O18 H2. And how many U am I going to get altogether? So 2.26 times 10 to the 14 times 22.07364 gives me 4.997. Actually, I'm only allowed 2 sig figs, so I'll just go 4.99 times 10 to the 15 U total. Did you guys get this? Yes? No? Punch it in your calculator. Make sure you get the same number as me. Setup looks fine. It's the mass of a single H2O18 H2 molecule. That came from a previous calculation. All right, the final thing is going to be another side calculation. And do you know the definition of the AMU or the U? What is it? No, that's the wrong definition. 12 grams is not the definition of the U. 12U of carbon 12, yes, is the weight of what? The mass of what? This is recall information. You know, we talked about this last week, and the way you're going to recall it is by seeing it over and over again. The more times you see it over and over again, the easier it is to recall. If the only time you're going to recall it is the night before the test, then forget it. You're probably not going to recall it for the test because your short-term memory is going to be overloaded. And so what you need to do is you need to look at it every day. And so somebody asked me about the study habits. You know, I reread my notes, you know, from day one to the present day, every day. And that's because my memory is so bad. If my memory wasn't so bad, maybe I could just look at it once and then remember it, but I don't. I mean, I look at the number here and I have to scroll back up because I can't remember it 5 seconds ago. That's how bad my memory is. And so, you know, if you want better recall, then and you don't have photographic memory, I recommend doing that. Just read it every day. It's 12U of carbon 12 per carbon 12 atom. This should be, I mean, this is like Chem 4 definition, and this was defined in Chem 4. So this is just review, and but it's easy to forget when you don't use it every day, and so you force yourself to use it every day, even though you don't really need to use it every day. But if you force yourself to use it every day, and it only takes a few seconds, then you have a better chance of remembering it. Okay, what's the definition of the mole? Okay, where did that number come from? Yeah, so there's 2. And where did Avogadro's number come from? 6.022 times 10 to the 23rd represents what? It represents the mole, Avogadro's number, but where did that number come from? What grams? How many grams? So this is the definition of the U, and then we have 2 things that define the mole. We call 1 mole is defined as exactly how many grams of carbon 12? Maybe you didn't catch this in Chem 4. 1 mole is defined as exactly 12 grams of pure carbon 12. You can get pure carbon 12. You just separate out the carbon 13 from it and the carbon 14, if any. So this is the definition of mole right here. 1 mole is defined as exactly 12 grams of carbon 12. And then how many carbon 12 atoms are there in exactly 12 grams of carbon 12? So Avogadro's number comes from this. And then the units canceled, and that leaves us with units of what? Okay, let's see. 12 cancels. Carbon 12 cancels carbon 12. This carbon 12 cancels that carbon 12. And the atoms cancel. This is atoms here. And what we're left with is this. There's 6.022 U per mole. No, actually not per mole. Mole cancels. What does it come out to? Sorry, mole cancels. Forgot to cancel that. And we're left with 6.022 times 10 to the 23rd. Got that. U per gram. All right, so our final calculation is here.
I don't think the units.
Which ones?
Or is it atoms also on top of the first one?
The U doesn't cancel, and the gram doesn't cancel, but everything else should cancel. So the atoms cancel. This is atoms on 12U of carbon-12 atom. It's just one atom, and the atoms cancel. If we invert this, then you get the book and you get the conversion factor in the book. Which one is easier to remember? The conversion factor in the book. The conversion factor in the book says that 1 U is equivalent to 1.6605 times 10 to the minus 24 grams. Which one is easy? This is only 5 sig figs here, but there are more. Usually most people use this to 3 sig figs, so let's just say 1.66 times 10 to the minus 24 grams in a U. Is it easier to remember how many U are in a gram or how many grams are in a U? It's a lot easier. I don't know why the book doesn't use this. All the books use this, including ours. And so what I'm going to do is I have the number of U, and it's a simple one-step conversion. So 1 gram is equivalent to 6.0226 times 10 to the 23rd U. And that's going to give me, I cleared it out of my calculator, 4.99 times 10 to the 15 divided by 6.022 times 10 to the 23rd gives me 8.286, or we'll just go with 3 sig figs, times 10 to the minus 9 grams. And then I'd probably use a metric prefix. What metric prefix am I going to use for this? I want to get rid of 10 to the minus 9. What is 10 to the minus 9 called? Nano? Nano? Would you agree? Yeah, that's correct. Micro is 10 to the minus 6. Nano is 10 to the minus 9. Are you guys, you already have those all memorized? Good. And so this is going to be 8.3 nanograms. So you just drank 8.3 nanograms total of the heavy water, the heaviest of the heavy water in that glass. Could you taste it? You couldn't taste it because it's going to taste like regular water. It weighs a lot more than regular water, but you can't tell in this mixture. All right, so that's using the mole concept, and that concludes chapter 2. And so what we're going to do is we're going to move on to chapter 3 now, which is supposed to start today, but I'm running out of time. Mm-hmm.
This is going to be the same like question that might happen.
Yes, this will be the same type of question. So this is another reason to go through the notes. If you can't do the calculations we did in lecture, then you need to work on that. You know, if like when I was asking about the earlier stuff, the percentages and that type of stuff, can you do those? If not, don't wait until the night before the exam to realize that, oh, I don't know what's going on here, because you're going to be in trouble. You know, this is why I say, like, you know, try to do it after class. Repeat the calculations. You might think, oh, that's easy. I have this old story, though, because when I was at UCSB, like, in chemistry, grad student, one of the professors there, I wasn't taking his class, but he was teaching a class. He was a theoretical chemist. He was teaching this class. There were only four students? No. I think there were 9 students. Yeah, 9 students in the class. It was a graduate level class. And he spent 4 days doing this calculation, something like that. And it was a very long calculation. And then he took a survey of the class. Did that make sense? Do you guys understand it? You know? And everybody said yes, it made sense. They understood it. And then the very next, lecture period, he gave them a test. It was a pop test, and it was just redo the calculation. And out of this class of 9 people, only I think 4 people were able to repeat the calculation. Five out of the 9 couldn't repeat the calculation. He'd just finished, and that everybody acknowledged that they understood. And so, you know, when you watch somebody do it, it's not the same. Watching somebody do it is never the same as doing it yourself. You know, sometimes people have a lot of experience and they know what traps to avoid. It's like you watch somebody lead you through the jungle, and they go very quickly. They take this path, they take that path, they take this path, and then the next day you have to repeat that. And then, did you really pay attention? You know, when it came to this fork, which fork do you take? The left fork, the middle fork, the right fork? And then all of a sudden you go, I don't remember. That kind of stuff. And so if you don't repeat these calculations, then you really don't know. And this is somebody else asked me, you know, should they focus on the homework or should they focus on the lecture? You focus on the lecture. You got to be able to do every single calculation we do in class. You know, before you start, you know, spending a lot of time going back through the homework, because the homework are going to be more specialized. But the homework is going to give you more variety, and that's what you need. You know, when you're beginning, you want to see a lot of variety and a lot of different types of problems.
So we would give you a graphing calculator?
No, officially the department policy is no graphing calculator. So you're supposed to use your backup calculator. Yeah. They have calculators. I don't know if I mentioned this, but you can check out a scientific calculator from the stockroom for the entire semester. They have a bunch of these. For Chem 1A, it's fine. For Chem 1B, I recommend getting a little bit better calculator than they have there. Yeah, no problem. Yeah, just make sure you can do these calculations. It might be totally confusing. If it's totally confusing, then work through it, you know. And if it's still confusing, then ask me in the next lecture to try to explain what's going on. So we're on chapter 3 now. But chapter 3 has a lot of memorization. Because chapter 3 deals with nomenclature and chemical compounds. We've already had some nomenclature, which I completely skipped, the nomenclature for the elements. But we're going to be looking at chemical compounds. You know, types of compounds. Do you remember the types of chemical compounds? Just a refresher. We have the ionic, molecular, covalent, we call them network covalent lattice, and that's pretty much it, I guess. We're going to deal with mole concept. We already did mole of the compound. The other one was mole concept regarding atoms, but I kind of skipped that. And so this was more of a, the one we just did was more of a 3-2, but the mole concept was introduced in chapter 2. Composition of chemical compounds, the formula, but there are different ways we can represent, like H2O. H2O you can represent using the elemental composition, 2 parts hydrogen, 1 part oxygen, or we can do it by the atom composition, 2 atoms of hydrogen, 1 atom of oxygen, or we can do it by mass. You know, it's 88% oxygen by mass, 11% or so hydrogen by mass. Or we could do it by atom, percent by atom. Percent by atom would be 67% oxygen, 33% hydrogen. So there are different ways of representing the composition. We want to know, what 3 things do we want to know about matter? We want to know its composition. Well, we want to know its properties, but how do we figure out the properties? There are 2 ways of figuring out the properties. One is just to measure all the properties. You know, if we measure all the properties, that's fine. You take a water sample and measure all the properties. Write them down. Boils at 100, freezes at 0, etc. The other way of trying to figure out the properties is by relating it to composition and structure. And so if we have some insight into the composition, because we don't want to have to measure every single thing. If you have to measure every single thing, it's going to be quite a burden. And so what we want to do is we want to look for patterns, or we want to understand some theories so we can predict it without actually having to measure it. And so there's certain things we do. So composition is one of them, structure is another one. So this is why we're interested in types. The types of chemical compounds have different types of structures. You know, molecular compounds have a different structure than ionic, which have a different structure than network covalent. And so those are the three types of structures that we're looking at. And there we can infer certain stuff. So for example, CO2 has molecular structure. SiO2, silicon, is in the same family as carbon. And this is one below carbon. But SiO2 does not have a molecular structure. You might think SiO2 has a molecular structure, just like CO2, another member of its family. But SiO2 is called quartz. CO2 is carbon dioxide. And SiO2 quartz, some people call it silicon dioxide. Some people call it silicon-4 oxide. How we name it depends, because do we use the rules for molecular, or do we use the rules for ionic? When we look for ionic compounds, those are typically metals and nonmetals. Well, silicon, is it a metal or a nonmetal? What is silicon? Silicon's at the border between metals and nonmetals, so we can use either set of rules. We can call it like a molecular compound, silicon dioxide, even though it's network covalent, or we can call it like an ionic compound, silicon-4 oxide. And we can use either. And so both are common for semi-metals. But anyway, based on its structure, SiO2 is totally different structure than CO2. It's going to have totally different properties. CO2 boils at a temperature well below room temperature, but SiO2 melts at a temperature way above. SiO2's melting point's over 1,000 degrees C. But continuing on with this, so we're going to get some idea about the composition. Now, the first thing in terms of structure we want to figure out, composition and structure in understanding properties, is oxidation states. Oxidation states will tell us a lot about the compound's chemical properties, its redox properties. And so we're going to look at oxidation state as the first tool in analyzing composition, and structure. We use oxidation states. And of course we analyze a lot of other things in addition to oxidation state. But oxidation state's an easy one that we can knock out quickly by just looking at the formula for the compound. And then we're going to get to naming, organic. We're going to do a lot more organic compounds this semester and inorganic. And so names and formulas of inorganic compounds. With that said, what we should do is we should start. I mean, it depends on how good your memory is. Do you guys remember all the polyatomic ions? You met some? Oh, that's good. So let's just review some of these. And plus, we're going to have some more polyatomics that I'm going to throw in there. So, 0903. So what polyatomics, let me ask you this. Do you know borate? Can you give me the formula for borate? Well, Ashley. Okay, good. And so I'm going to start off at the back so we have more time to memorize this. But let's take a look at the polyatomic anions. The polyatomic anions that end in 8. And so these are the ones you just have to straight out memorize. You need to memorize borate. Silicate. What's the formula for silicate? Yes. Silicate is SiO4 4 minus. And then there's some others that we need to just outright memorize. And however you memorize these, you could look for patterns or whatever else, but things like, and these are in no particular order, chromate. What's the formula for chromate? Yes. Chromate is that. Dichromate. CrO7 minus 1. It's getting close. Cr2O7 charge? 2 minus. Good. Dichromate. What are some other 8s? Permanganate. Permanganate. MnO4 minus. Chromate, dichromate, permanganate. Carbonate, you don't have to memorize. You have to know. Cyanate. Cyanate is not that common. We'll do.
CN
Cn minus. Cyanide. Oh, with the 8s, I'm saying. ATE ending. How about oxalate? Do you know that one? C2O4 2 minus. That's good. How about acetate? Yeah. Maybe a few others. Cyanate is not that common, but we'll throw it in here. SCN minus. This is thiocyanate. No. OCN minus is cyanate. These ones you don't need. Can you start working on these to memorize? If you don't already have them memorized. All right, we're done with time, so thanks. OCN and SCN. The bottom two are SCN and OCN minus.